Okay, let's talk quickly about mixture of experts, why we need it, and two of its most common variants. So why we need mixture of expert is we want to increase the capacity of the model and hence the learning ability of the model without linearly increasing the cost, right? So the cost is very important factor in designing the neural networks for training but also for inference. And the idea of mixture of expert is we increase the number of parameters like this. We have number of experts which can just be feed forward neural network, but at runtime we choose only k of them, right? For example, we can have n experts and n can be 32 or 64 or 18, but at runtime each input passes through few of them, and I will show how we select those few. Okay, let's go through this DeepSeek paper, auxiliary loss-free load balancing for mixture of expert. And the idea of going through it is it will also introduce mixture of experts, and we will implement exactly the same thing in the code. And then I will also talk a little bit about what this loss-free means and why we need the loss function at all here. Right. So this is the mixture of expert. Like I mentioned, it is the same implementation. So given ut is the input, so it takes the sum of input pass through the feed forward neural network multiplied by the gating score. And the gating score is you select the top k out of the n experts, right? And this score is defined by this GUTE, right? So G can be any nonlinear function, but normally it's just a softmax function, right? So you can think of these as the probability scores for each expert, and then you select the top k experts from there. We pass the input through those selected top k experts, multiply their score with it, and take a sum of it. So that's how mixture of expert work. So one of the problem with mixture of expert is the routing collapse. So you can think about if all of those tokens, input tokens, are passed to the same experts, so that will lead to the routing collapse because none of the other experts are utilized properly and they will not learn anything useful. So to avoid that, we want to balance the input loads among the experts, right? And this is how the normally the auxiliary loss for MOE is defined, and it encourages to distribute equally the tokens among different experts, right? And we can go through what this equation does is basically the summation from I to n, where n is the number of experts. We multiply f of I multiplied by p of I. So f of I is the fraction of tokens routed to expert I, and p of I is the score of that expert. We can look more into what this does is for all the tokens, so number of tokens are t, from 1 till t it is 1 if that token is selected for that expert, right? And it divided by kt by n, right? So if we look into, we have t number of total tokens and we want to assign it to k experts, right? So the total number of assignments are t into k, and then the total number of experts are n. So the ideal assignment of tokens for each expert will be kt, these are the number of assignment, divided by n, right? So whatever we have for each expert, we divide by kt by n, and this n goes up, and then you can just write this equation like this. P of I is just the average score which was assigned to that expert for all the tokens, and we just multiply it and we sum it all up. So what DeepSeek paper showed that this auxiliary loss, which encourages a balanced distribution of token among expert combined with the large language model loss, which is cross entropy on next token prediction. So when these two losses are combined, and then we do a backward pass and update the model with gradient descent, so their gradients have conflict, and this auxiliary loss actually hinders the performance of language model. And the loss-free load balancing is quite simple. So all they do is before we do the nonlinear function, we add a bias term to it, right? And we just adjust this bias term so that we have a proper load balancing. We don't calculate the loss and do the gradient and then pass it through the whole network. Like I mentioned, they showed that auxiliary loss strategy and updating gradients based on auxiliary loss hinders the performance of language model. Let's just go through the code and see how both the MOE based on auxiliary loss and MOE based on auxiliary loss free implementation works. So the first thing is the expert. So this is how we define the expert. It's just a feed forward neural network. It's in module list, and the length of the list is the number of experts. Then we define the centroids, one for each expert, and the idea of it is to basically calculate the score for each expert. So this is used for the gating function or scoring function. Let's go to the forward pass. It's quite simple. UT is the input of size, batch size, sequence length, and dimension. K is the number of experts that we want to select. N is the total number of experts. Total token is batch size multiplied by sequence length. So we flatten the first two dimensions, right? So this is what's happening here. We calculate the gating score by multiplying the input, which is flattened, and multiply by the centroids, which is to calculate the gating score. We pass the scores through the softmax function, and then we select the top case scores, and then we select the top case scores and the top k indexes. So those indices will be used to route the tokens through. So the next few steps is used to basically do this more efficiently, right? Remember, what we want to do is loop through each of these tokens, pass it through k of the selected experts that we get from top k, and get its output. But looping through each of the token is very slow, and we can do it using some tensor manipulations and matrix multiplications. What we do is repeat the u flat k times, right? So because we want to select k expert indices for each of the input, so to pass it efficiently, we repeat it k times, and the output will be the same size as this repeated, right? So both the flat inputs, which is repeated, will become BSK. So remember, BS tokens need to pass through k experts, right? So that's why we have repeated it k times, and the output shape will be again the same, BSK cross dimension. Okay, so now we want to calculate the loss, and we just check if we are in the training, then we calculate the loss, otherwise we don't. So what we are trying to do here is to calculate Fi and Pi, like mentioned here, Fi and Pi. Again, what we're trying to do here is calculate Fi and Pi, and Fi are the fraction of tokens routed to expert I, and Pi denotes the average score of that expert I. So first we do the one hot encoding to number of classes n. So what it will do is reshape BSK vector to BSK cross n. So it will be 0 everywhere except wherever that index was true. So if that index was 1, so it will be, and we have the 0 index, so it will be 0, 1, and the rest of the n will also be 0, right, and so on. So we convert it to one hot encoding, and we just take the sum across the 0 dimension, and it will do exactly this then, right? So we take the sum for all the tokens, and then we divide it by the ideal load, right? Ideal load is again kt by n, and this is just an n has gone up due to division. And pi is just one hot multiplied by flat values, and values are also coming from here. These are the top k values which were flattened. So it will again be 0 everywhere except for the index that it was selected, and it multiplies that index by the actual value. We sum it across the 0 dimension and divide by the t. This is again exactly the same equation as written here. And then the load balance is these two multiplied and sum across the first dimension now. And this is what's happening here. These two multiplied, sum it up, and alpha multiplied by alpha. So this is alpha of that auxiliary loss, right? And then we can also keep track of the maximum load violation, right? So in DeepSeek paper, there are two kind of maximum load violation. One is for batch, one is for the global. I have implemented here batch. For each batch of token, how many violations we have. Again, the perfect load we have is kt by n. Kt is the number of assignments, n is the total number of experts. And what we want to track here is get the maximum of f of I. F of I is the number of tokens assigned to each expert. So if we can get what was the maximum number of tokens that was assigned to any expert, that can be the maximum violation which we are interested in. And then we can minus the perfect load from it divided by the perfect load to create this metric of maximum load violation. And this is where we are calculating the output. And essentially what we are doing here, get all the tokens which were assigned to a particular expert, pass it through that expert and assign it to the output. And all of this masking and this repeating allows us to do it efficiently. Right. So you can actually do it more efficiently with some more tensor interpolation, but I don't want to do it. I have to still make it more readable. But this is still better than very naive implementation. Otherwise, you will require two loops. You will have to pass through each token and then for each expert. So I removed one of the main bottleneck of passing through each token, but we still have to pass through each unique experts. Right, so here then our output shape is BSK dimension. Remember the input was BS dimension, and we also want the output to be of the same dimensions as the input. So for all of these experts K, we will multiply them with their gating scores, these G's, and then sum it up across this second dimension. So we are left with BS dimension, which is the same as input, right? And what happens for the auxiliary loss based training is that we pass this loss also that we have calculated, right? We calculate the backward pass, we calculate the gradient, and then we update the parameters of the model. And then to quickly go through the lossless, it's very simple. It's exactly the same. The only thing is we will not return any auxiliary loss, but we will, how the experts will be selected is based on the changes in biases. So this thing is exactly the same. We only add these biases whose size is the same as the number of experts, and we don't want to train it or calculate this gradient. We will manually update these biases in the below loop. So that's why it's registered as buffer. So all of this is exactly the same as the previous one. The only thing different is here. Now the scores, and scores, remember, will be used in top case selection, and we add these biases in the scores. And in this way, by changing these biases up and down, we can change the experts which were selected, because remember these scores were used to select the top K experts. After adding the biases to the score, it again passes to softmax. We select the top K, it's exactly the same. The only thing is how to update the biases, right? Remember, the idea is for all the tokens to be equally distributed across all the experts. That's the ideal case, right? So we first calculate the perfect load. Again, it's KT by N. KT is the total number of assignments, N is the total number of experts. We have F of I, which is the number of tokens assigned to each expert. So we do this one hot and then we sum across the zero dimension for all the tokens. So this will give you how many tokens were assigned to each expert actually. We subtracted perfect load minus F of I, and this is our error. And we want to update the bias by the sign of this error, right? So you can think of it is in this way. So if perfect load is greater than the current assignment to the expert, so this thing will be positive, and we will add in the score of biases. So it will assign it more scores, so more tokens will be assigned to it, and vice versa. If it is less than the current assignment, this error will be negative and we decrease the biases, so we assign it less number of tokens. And then we calculate the output, exactly the same. Outputs are multiplied by the actual scores, and we return the output and the maximum violations. So maximum violation is just for tracking how many violations we have for the current batch. Again, it can also be calculated globally, but we are doing it for each batch, and we return the output. So in this way, we have covered mixture of experts. We have also covered the two most famous version of it, auxiliary loss based and the lossless. And the DeepSeek has shown the lossless is much simpler, much better, doesn't interfere with the language model objective function, and also obtains much better load balancing, right? So this red is for loss free, blue is for auxiliary loss space. You can see we have much lower maximum violations here, right? So yeah, that's it. Think of mixture of expert as how to increase the capacity of model without linearly increasing the computation costs. So we can just select some of the experts from the total capacity of the model. One thing we have to be careful about is routing collapse, and then there are two ways to do it. One is based on auxiliary loss, second is loss free. When deciding to choose between loss based and loss free, I will start always with loss free because it does not interfere with the gradient calculation of the overall loss function. And many of the newer work like GLM 4.5 is also using this loss free mixture of experts. Yeah, if you need more detail, I have a Substack article on this. Okay, see you next time. Bye.